Greetings. Welcome to section 1.3, Vector Equations. I'm going to take a moment and apologize right now for the nasally voice I have. I think my allergies are kicking in, so I apologize. In this section, we are going to begin to connect equations involving vectors to ordinary systems of equations. And for now, don't get all hung up on the term vector. Right now, we are just going to think of a vector as an ordered list of numbers. And here on this slide, you were provided three different examples of a vector. The set of all vectors with two entries, like these above, are denoted by this symbol here. And this is just read R2. Just like any other math class, this symbol represents real numbers. And then the exponent 2 simply indicates that there are two entries in those matrices. And it's pretty straightforward to know that two vectors are considered equal if their corresponding entries are equal. So if I have this matrix, it's important to know that it is not equal to this matrix because the entries are different. Yes, the numbers are the same, but the entries themselves are different. This slide here basically shows you some examples of vector addition and scalar multiplication. And all we do is we either add, subtract, multiply those corresponding entries. So take a moment, pause this, and I think that you will find that this is straightforward. So let's take a look at these examples here. When we type, a vector is bold-faced, but when we write a vector, sometimes we will put a little arrow on top of the letter to indicate that that represents a vector. So if I'm adding vector u and vector v, I'm going to show my work in this way. And what I'm going to do to get my answer is I'm just going to add the corresponding entries. So 3 plus 2 is 5, and then 2 plus a negative 1 is 1, and we end up with the following vector. Suppose I want to do the next example, u minus 2 times vector v. I can set this up in the following way. So the first thing I may want to do is this piece here. So I'm just going to rewrite the first vector, and then I'm going to use scalar multiplication to get this next vector. And then I'm going to subtract. So it'll be 3 minus 4, giving me a negative 1 in my first entry, and then 2 minus a negative 2, which is a positive 4. I think you'll find that this is not super complicated. There is a parallelogram rule for addition, which is stated here, but basically what I've shown you is vectors can be graphed. So, and I'll kind of show you this in the next slide a little bit, but basically the vectors that are given to us correspond to an ordered pair. Well, I'll just show you here. So if I have this vector, this corresponds to the ordered pair negative 3, 1. So I would plot that and draw in this arrow, which represents a vector. So I have two different vectors here, and if I want to add them together, it gives me this vector here, which is found by basically finding the length of the diagonal of a parallelogram. Now, there's actually a pretty interesting real life example on this video. When I found this, I thought it was pretty interesting, so you might want to take a moment and just watch that. So we can geometrically visualize these vectors, just like I showed you on the previous slide. So this represents the ordered pair -3, 1, but as a vector, we will write it in this way here. Vector v can be written in a similar manner. So it just kind of depends on how many entries we have. If there are n entries, then we will have an n by 1 column matrix. Here is a list of algebraic properties. Some of them we've already touched on, but they're really pretty straightforward. So go ahead and pause and take a brief look at these properties. So we're going to come up with some new terminology and some new definitions. But basically, if I have these vectors and these scalars, what I can do is create what we call a linear combination. And I'll just take a scalar times a vector plus a scalar times a vector plus so on and so forth all the way down. The scalars are known as the weights. So a linear combination can be any real number including 0, and we'll see lots of different linear combinations of these. The first example that I have here is something that you will see in your homework. And basically it says that this figure identifies selected linear combinations of these two vectors. So if I look at this, V1 is right here. Let me change colors. V1 is right here, which is the ordered pair -1, 1. Okay. And then V2 is over here with a different ordered pair. Okay. So what we're going to do is estimate the linear combinations of V1 and V2 that generate these two new vectors. Okay, so this terminology is a little bit different, but we are basically going to apply the parallelogram rule. And I'm just going to draw those in. So let's first identify where vector u is. Vector u is way over here. And what I want to do is I want to create some parallelogram where I can use this given information and write a linear combination. So when I do this, I'm just going to draw in this parallelogram and analyze how we get there. Okay, so if I look at this, I can say that vector u comes from the following. If I look at this point here represents 3 of this vector 1. So to get from the origin to vector u, I have 3 of vector 1, and I will add that to, green, in the opposite direction to get here, -2 V2. So remember, the parallelogram rule says I can take these two vectors, the one in purple and the one in green, and the middle, the diagonal, gives me the new vector. Okay, so that is the linear combination of vector 1 and vector 2 that generate vector u. Now I'm going to erase this and we're going to do the same type of thing with vector w. Alright, so let's identify where vector w is. That is right here. So if I look at this, I can sketch in this parallelogram that's around it. Okay, and this will maybe help me identify how to come up with that. Now, if I look at this, starting with V1, it looks like this is the distance, which is really 2.5 or 5/2 of vector 1. I'm going to add that to, if I look at this looks like it's half of negative V2, so a negative 1/2 of vector 2. So if I have this vector and this vector, by the parallelogram rule, the sum of those vectors equals vector w. So this is the linear combination of vector 1 and vector 2 that generates vector w. This here just illustrates another real-life example of linear combinations, but this involves 3 different vectors. If this is something you're interested in learning more about, take a look at this website here. Okay, so let's get to the good stuff. Here I have 3 different vectors, and we want to determine whether vector b is generated or can be written as a linear combination of a1 and a2. So what this means, in other words, we want to figure out the weights, x1 and x2, that will provide us with vector b. Okay, now I know that seems like a lot, but we'll find that there are different ways a question can be asked, but it's asking the same thing. Okay, so basically what we're going to do is we're going to set up a matrix. We are going to row reduce to solve. If we end up with a solution, then the answer to this question is yes. B can be written as a linear combination in this manner. Okay, so on the next slide, I'm going to show you. Okay, so here we go. Here is the question, and what we are wanting to do is we want to find the following. We want to find the x1 that we multiply by a1 and add it to the x2 multiplied by a2 to get b, which is this matrix here. Okay, well, these are just scalars, so what I'm going to do is multiply these here. And when I do, I get the following matrices. x1, negative 2x1, negative 5x1, plus 2x2, 5x2, 6x2 is equal to 7, 4, negative 3. All right, well, moving on, I can add these in the following way to get x1 plus 2x2, negative 2x1 plus 5x2, negative 5x1 plus 6x2 And this needs to equal, again, matrix B, 7, 4, negative 3. Okay, well, really, what this is a system of equations. I know that because this can be written as x1 plus 2x2 is equal to 7, negative 2x1 plus 5x2 is equal to 4, and negative 5x1 plus 6x2 is equal to negative 3. So if I have this system of equations, I can write that as an augmented matrix to solve. So if I represent that as an augmented matrix, I'll simply take the coefficients and what they're equal to and write that as a matrix. So that will be 1, 2, 7, negative 2, 5, 4, negative 5, 6, and negative 3. Does this look familiar? It should. So we started with something that looked different. The question was something different than what we've seen, but ultimately it ends up being the same thing that we had in the previous section. So now what we're going to do here is row reduce and solve. So we know that we want this entry to be 1, which it is. So that's going to be a pivot. Remember, everything below that needs to be 0. So in order to make that happen, I'm going to take 2. Oops, I'm going to use a different color. I'm going to take 2. Really? Oh, for heaven's sakes. 2 times row 1 and add that to row 2. That's going to become my new row 2. So I'm going to keep row 1 as is, but now with this operation that I have stated here, my row 2 will change, and it will become 0, 9, 18. I'm going to do the same type of thing for row 3, but this time I'm going to take 5 times row 1 plus row 3, and this will become my new row 3. And it becomes 0, 16, 32. All right, now I want you to remember that our pivots should be a 1. So I want to make that a 1. And the way I do that is I take 1/9 times row 2, and that will become my new row 2. So 0, 1, 2. And row 1 and row 3 remain the same. Moving right along, now that I have another pivot, I want everything above and below that to be 0. So that's what I'm going to work on now. So when I do this, I'm going to kind of do this as a twofer. I'm going to take negative 2 times row 2 and add that to row 1 to get my new row 1. And when I do that, I'm going to end up with 1, 0, 3. And then I'm also going to do negative 16 times row 2 and add that to row 3 to get my new row 3, which happens to be 0, 0, 0. Row 2 remains the same, 0, 1, 2. Okay, so let's look at this here. I have 2 pivot positions here and here. Nothing extraordinary is happening in this last row. So what this is telling me is that x1 is equal to 3 and that x2 is equal to 2. So what I can do is jump back up here and replace x1 with 3 and x2 with 2. So if I do that, I have 3, times the matrix here plus x2, which is 2, times this matrix here is equal to this matrix. You can go ahead and check it. And to do that, you'll multiply everything here by 3, everything here by 2, and then add them to get this matrix here. And you should find that it works out. Not so bad, right? So we have solved this question, and we can write B as a linear combination, which is here. So, you know, I want to come back real quick to this matrix here, the one we started with. Okay, so I'm just going to rewrite that right here because I want to show you something. This matrix here has columns A1, A2, and B. This is column A1, column A2, and column B. So we can represent this as the matrix A1, A2, and B, which leads me to some new notation. This vector equation, which is kind of what we had before, has the same solution set as a linear system whose augmented matrix is this. In particular, B, this, can be written as a linear combination of vector 1, vector 2, so on and so forth, if and only if the system is consistent. So we have a definition, which is here. And there is something new, and that is this. It's called a span. Basically, a span is the collection of all vectors of the form C1, V1 plus C2, V2 plus so on and so forth, with these guys being the scalars. So depending on what the scalar is, the scalar can be anything. We will have lots and lots and lots and lots of different linear combinations. So this here represents all of those, and it's called the span. For example, this is a typo. This should say V. So this is just kind of a visual form. Basically, the span of V represents all multiples of this vector. So depending on what this vector does, it could have lots of different multiples. That represents the span of one single vector. But then the span of UV is everything in this plane here. So it just depends. Oops. It just depends on what multiple of these vectors we're choosing. Okay. Okay, let's look at this example here. So another basic problem is to determine if this given vector is in the span of this set of vectors. So this is just another way of asking a question. So basically, we want to know if vector B is a linear combination of these three vectors. In other words, does the following occur? Does x1 times this vector plus x2 times this vector plus x3 times this vector equal vector B? Okay, so what we'll do is we will set up an augmented matrix, which just becomes these guys all together. And I showed you where that came from in the previous example. So I'm just going to kind of skip distributing and writing that system of equations and so on and so forth, and just jump straight to the augmented matrix. Okay, so here's what we have, and it appears I've already messed up my signs. 1, -2. All right, so you might want to double check that you have your matrix written correctly. And again, this should be a -6. See how easy it is to make mistakes? Okay, so what we're going to do is we're going to row reduce, see what happens. So we're in good shape because my very first entry is a 1. So that is a pivot. Remember, everything below that also needs to be a 1. So the first thing I'm going to do is change this. So I'm going to take 2 times row 1, add that to row 2, and this is going to become my new row 2. So row 1 remains the same, but row 2 becomes 0, 1, 4, and 5. And, you know, as you're watching these videos, you may want to pause, try to come up with this same row 2, and then unpause and see what happens. Row 3 remains the same. Okay, so now I notice I have a pivot, and this here second pivot, I have a 0 above it. Now I need to make sure I have a 0 below it. So to make that happen, what I'm going to do is I'm going to take -2 times row 2 and add it to row 3 to get my new row 3. So rows 1 and 2 remain the same, but row 3 will become 0, 0, 0, -16. Now, you may remember from the previous section that we cannot have a pivot in this last row here, or last column rather. This tells us that we have no solution, because there's no way that 0 will equal -16. Because this augmented matrix has no solution, we can draw a conclusion about this statement here. We can say that B cannot be written as a linear combination of the other 3 vectors. There you have it. Not so bad, right? All right, let's look at another example. Okay, so here I've told you what 3 different vectors are, and you may notice that in vector B, it's a little bit different. I have one entry that is a variable. What I want to do in this case is find the value or values of H that allow B to be spanned by vector A1 and vector A2. So basically what this is saying is the following. Does the equation x1 A1 plus x2 A2 equal B have a solution? Okay, so does this linear combination have a solution? And the way we solve that is by setting up an augmented matrix, row reducing, and solving. So everything is the same, just different words. So I'm going to set up my augmented matrix, making sure I have all of my entries written correctly this time. Why don't you go ahead and pause this in row reduce and see if you end up getting the same thing. Hopefully you notice that our first entry is 1. Everything below that needs to be 0. So I'm going to take -4 times row 1, add that to row 2. And I'm also going to take 2 times row 1, add that to row 3. So our new matrix becomes the following. Now this last entry is a little bit different. It is going to be 8 plus h, or h plus 8. This is a variable, so we won't have like terms, so we are going to leave it as is. This is a pivot. I want to make that pivot 1. So the way I'm going to do that is by taking 1/5 times row 2. So my new matrix becomes the following. All right, now we want, so we have 2 pivots. We want this to be a 0, so I'm going to first, wait a second. I have a typo. Hopefully you noticed that this should really be a 3. I apologize. Sorry. Okay, so we want that 3 to become a 0, and the way we correct that is by taking -3 times row 2 plus row 3 to get the new row 3. So we end up with the following. This becomes 0, 0, 17 plus h. Okay, now I apologize for my cold or allergies or whatever it is. Now here, this is where we need to analyze this. Now looking at this, we need to be very careful. We know that this here cannot be something other than 0. If 17 plus h, if this entry is something other than 0, we will have no solution in this augmented matrix. And that means that the plane spanned by vector 1 and vector 2 will not have any values of h to allow for this to be true. So we can say that B is in the span of A1, A2 when 17 plus h equals 0. Because if that is equal to 0, 0 does equal 0, and we're happy. So, therefore, 17 plus h equals 0. If I solve this, that means h is equal to -17. So to answer the question, the value of h is -17. This is the last example that I want to show you in this section, and it happens to be a real-life example. You'll find that in the business world, there's a lot of matrices involved. And this is just one example of how it works. I'd like you to pause this and read through this example and understand what's happening. So in this example, we basically have 2 different products, product B and product C. And these matrices represent the cost what the company spends on different things. So the first thing we want to do in part A is give some sort of interpretation of what this vector represents. And basically, 100B represents the various costs for producing $100 worth of product B. And hopefully you came up with that on your own. So we can elaborate a little bit more and say that 100B is equal to 100 times this matrix. And if I distribute that 100 to everything here, I end up getting a new matrix, which is this. Sorry for my poor handwriting. And this represents different things. This tells us that in order to produce $100 worth of product B, we will use $45 for materials, because that's what the first entry represents, $25 on labor, and $15 on overhead. And that's basically how you interpret these matrices. So in part C, it says, suppose the company wishes to manufacture $X1 worth of product B and $X2 dollars worth of product C. Give a vector that describes this. So really, it's pretty straightforward. Don't make it harder than it has to be. We'll write the linear combination X1 times B plus X2 times C. And that's it. And this concludes section 1-3.